One planet in our solar system breaks every rule. Uranus lies completely on its side. Every other planet spins like a top. Uranus rolls like a barrel. Tonight we're uncovering the catastrophic collision that created this cosmic oddball. We'll trace how this sideways world survives impossible seasons and twisted magnetic chaos. Before we explore this tilted ice giant, drop a comment about your favorite planetary mystery. If you enjoy these cosmic detective stories, consider subscribing. Picture our solar system, 8 planets spinning upright like elegant dancers. Then there's Uranus. This ice giant lies on its side, completely sideways. When planets form, they're supposed to spin upright like Earth does. Uranus ignored this cosmic rule entirely. The planet's rotation axis tilts 98 degrees from normal. That means it's lying almost flat on its back. Imagine Earth lying on its side. That's what happened to Uranus. Everything about this world reflects its bizarre orientation. Its moons don't orbit around the planet's middle like normal moons do. Instead, they circle around the sideways equator like a Ferris wheel standing on edge. This creates the strangest seasons in the solar system. Each pole gets continuous sunlight for decades, then plunges into decades of total darkness. No other planet experiences anything close to this extreme. For billions of years, Uranus has maintained this sideways dance through space. Something knocked it over permanently. Scientists have a leading explanation for Uranus's sideways spin. A massive object struck the planet billions of years ago. This wasn't a small asteroid. It was roughly the size of Earth. Computer simulations recreated this ancient disaster. The impactor slammed into young Uranus at tremendous speed. Instead of destroying the planet completely, it knocked Uranus sideways and kept going. This collision happened during the solar system's most violent period. Giant objects regularly crashed into forming planets back then. Most planets recovered from these impacts. Uranus never did. The crash may explain many strange features of Uranus today. The impact could have blasted material into space that became the sideways moons. It may also have scrambled the planet's interior, creating a magnetic field that points in the wrong direction. Possible evidence for this collision may hide in Uranus's atmosphere. The planet may contain chemical signatures linked to the impacting object. These materials may have mixed into Uranus's atmosphere long ago. Uranus represents a cosmic crime scene preserved for billions of years. A permanent reminder that planetary formation was far more violent than we imagine. Every planet with a magnetic field follows the same rule. The magnetic poles line up roughly with the spinning poles. Uranus breaks this rule spectacularly. The planet's magnetic field tilts 60 degrees away from its rotation axis. That's like having a compass that points sideways instead of north. Even stranger, the magnetic center doesn't line up with the planet's center either. This creates the most chaotic magnetic environment in the solar system. As Uranus rotates, its magnetic field corkscrews through space. The field's strength changes dramatically every few hours. Scientists think the ancient collision scrambled Uranus's interior completely. Most planets generate magnetism in their cores. Uranus apparently creates its magnetic field in the outer layers instead. This twisted magnetism affects everything around the planet. Solar wind particles get trapped in bizarre patterns. The planet's moons experience constantly changing magnetic conditions. Even the aurora displays would look completely alien compared to Earth's. For spacecraft visiting Uranus, this magnetic chaos presents serious navigation challenges. The field provides no reliable reference point for direction. Uranus experiences the most extreme seasons in the solar system. Each season lasts 21 Earth years. That's longer than most human careers. When summer arrives at one pole, that region receives continuous sunlight for decades. No sunset, no night. Just endless daylight heating the same area year after year. Meanwhile, the opposite pole endures equally long winter darkness. During these extreme seasons, temperature differences should be enormous. The summer pole should be blazing hot. The winter pole should be frozen solid. But Uranus defies this expectation too. The planet somehow maintains nearly equal temperatures everywhere. The winter pole stays almost as warm as the summer pole. This shouldn't be possible according to basic physics. Scientists suspect the planet's thick atmosphere redistributes heat around the globe. Powerful winds carry warmth from the heated regions to the dark areas. This creates a planetary heating system unlike anything else in the solar system. For anyone living on Uranus, the concept of normal seasons would be meaningless. You'd experience the same season for your entire lifetime. Most giant planets glow with internal heat. Jupiter radiates more energy than it receives from the Sun. Saturn does the same. Uranus breaks this pattern completely. The ice giant emits almost no internal heat. It radiates roughly the same amount of energy it absorbs from sunlight. For a planet this massive, that's nearly impossible to explain. All giant planets should generate heat from their formation. When these worlds first assembled, gravitational compression created enormous internal temperatures. This heat should still be leaking out billions of years later. The ancient collision may have disrupted Uranus's ability to retain heat. The impact could have scrambled the planet's interior so thoroughly that heat escapes through unusual pathways. Or perhaps the collision actually removed heat from the system entirely. This heat deficiency affects the planet's entire structure. Without internal heating, Uranus lacks the powerful atmospheric storms that characterize other giant planets. The weather systems remain relatively calm and predictable. Uranus essentially runs on solar power alone. This makes it the coldest giant planet despite not being the farthest from the Sun. Uranus doesn't just spin sideways. Its entire family of moons and rings lies sideways too. This creates one of the strangest orbital systems in the solar system. The planet hosts 27 known moons. Every single one orbits around Uranus's tilted equator. When viewed from Earth, these moons appear to orbit vertically like spokes on a wheel standing on edge. The ring system adds to this bizarre geometry. Uranus has narrow rings that encircle the planet's sideways middle. These rings stand nearly vertical in space, creating a cosmic hula hoop effect. This sideways arrangement supports the collision theory. When the ancient impact knocked Uranus over, it carried the entire system with it. The moons and rings retained their positions relative to the planet's equator. The largest moon, Titania, experiences the same extreme seasons as the planet itself. Half of its orbit takes place in continuous sunlight, while the other half occurs in total darkness. No other moon system experiences such extreme seasonal variations. For spacecraft approaching Uranus, this sideways architecture creates unique navigation challenges. The traditional concepts of above and below become meaningless. Uranus possesses the calmest atmosphere of any giant planet. This shouldn't be possible given its extreme seasonal heating. The planet should experience massive storms and violent weather systems. Instead, it remains remarkably tranquil. The atmosphere consists mainly of hydrogen and helium, like other giant planets. But Uranus contains more water, methane, and ammonia ices. These materials give the planet its distinctive blue-green color. Even during the most extreme seasonal heating, Uranus generates surprisingly few storms. Other giant planets display massive hurricane systems and powerful jet streams. Uranus shows only subtle cloud formations and gentle atmospheric circulation. Scientists think the planet's lack of internal heat contributes to this atmospheric calm. Without energy rising from the interior, weather systems lack the power source needed for violent storms. The atmosphere relies almost entirely on weak solar heating. This atmospheric stability makes Uranus one of the most predictable giant planets. While Jupiter and Saturn display constantly changing storm systems, Uranus remains relatively uniform. The planet's weather changes slowly and subtly over decades rather than days. For meteorologists, Uranus represents an alien type of atmospheric behavior that challenges our understanding of planetary weather systems. Only one spacecraft has ever visited Uranus. Voyager 2 flew past the planet in 1986, providing our only close-up look at this sideways world. That brief encounter revealed more questions than answers. Future missions to Uranus face enormous challenges. The planet lies so far from Earth that spacecraft take decades to reach it. The journey requires perfect timing to use gravitational assists from other planets. Scientists are planning an ambitious orbital mission to study Uranus for years instead of hours. This spacecraft would map the planet's interior structure, study its twisted magnetic field, and monitor its extreme seasonal changes in real time. The mission would also investigate Uranus's mysterious moons and rings in unprecedented detail. Some of these moons might harbor subsurface oceans that could potentially support life. Understanding Uranus has implications far beyond our solar system. Astronomers have discovered thousands of similar-sized planets orbiting other stars. Many of these worlds might have experienced similar collision histories. Uranus serves as a laboratory for understanding how planetary catastrophes shape world development. The lessons learned from this tilted ice giant will help us understand planetary evolution throughout the universe. Nothing in normal planetary formation can create what happened to Uranus. The physics simply do not work. Small impacts and gradual changes cannot flip a massive planet completely sideways. Scientists calculated the energy requirements for Uranus's current state. The numbers are staggering. Only a collision with an Earth-sized object moving at tremendous speed could deliver enough force. This energy calculation is called angular momentum transfer. Think of a spinning ice skater getting hit by a bowling ball. The skater would tumble completely out of control. That is exactly what happened to Uranus billions of years ago. Alternative explanations fail completely under scientific scrutiny. Multiple small impacts would never add up to the required energy. Gravitational interactions with other planets are far too weak. Even close encounters with passing stars could not generate enough force. The collision scenario remains the only explanation that matches the observed physics. The evidence points to a single catastrophic event rather than gradual change. Why did this massive collision happen in the first place? The answer lies in the solar system's most violent period. Scientists call this era the Late Heavy Bombardment. 4 billion years ago, giant objects regularly crashed into planets throughout the solar system. The moon's cratered surface preserves evidence of this cosmic shooting gallery. Earth experienced similar bombardment, but geological processes erased most traces. During this chaotic period, planetary-sized bodies roamed freely through space. These objects were leftovers from the original formation of the solar system. Gravity had not yet cleared them into stable orbits. Uranus formed during the tail end of this violent era. The planet had just finished accumulating most of its mass when the impactor struck. This timing helps explain why Uranus survived the collision instead of being completely destroyed. Earlier impacts would have disrupted the planet's formation entirely. Later impacts would have been deflected by Uranus's established gravitational field. The collision occurred during a narrow window of planetary vulnerability. Uranus's atmosphere may contain chemical evidence of the ancient collision. The planet's composition does not fully match what scientists expect from simple formation models. Foreign materials may have entered the system from elsewhere. The most telling evidence involves isotope ratios. These are different versions of the same chemical elements. Every region of the solar system can carry a distinct isotopic signature, like a cosmic fingerprint. Uranus shows isotopic ratios that may point to mixed origins. The planet may contain materials that came from objects that formed farther out in the solar system. These foreign signatures could have mixed into Uranus's atmosphere during the collision. Computer models can recreate these chemical patterns by including a massive impactor. The simulations show how collision debris could have become incorporated into the planet's atmospheric composition. This chemical evidence provides forensic-style support for the ancient catastrophe. Like DNA evidence at a crime scene, these isotopic signatures point back to what may have happened billions of years ago. The collision had to occur at exactly the right angle to produce Uranus's current state. Too direct and the planet would have been shattered. Too glancing and the impact would not have changed the rotation significantly. Scientists determined the optimal impact angle through detailed computer simulations. The collision occurred approximately 45 degrees to Uranus's original rotation axis. This angle delivered maximum rotational change while preserving the planet's structure. The impactor approached from a specific direction that maximized the angular momentum transfer. Think of hitting a spinning top with a stick at just the right angle to make it wobble sideways without stopping its spin entirely. This precise geometry explains why Uranus tilted instead of fragmenting. The collision imparted enough energy to flip the planet sideways, but not enough to overcome the gravitational forces holding it together. The surgical precision of this impact represents an incredibly unlikely cosmic accident. The odds of such a perfect collision are astronomically small, yet it clearly happened. What happened to the massive object that struck Uranus? Scientists believe most of it became permanently incorporated into the planet itself. The impactor did not bounce off or shatter into pieces. During the collision, the impactor's material merged with Uranus's existing mass. High temperatures and pressures from the impact melted and mixed the two objects together. This process is called accretion. The merged material may explain some of Uranus's unusual internal structure. The planet's density and composition may reflect contributions from both the original Uranus and the foreign impactor. This hybrid nature may affect everything from the magnetic field to heat generation. Traces of the impactor may persist throughout Uranus's interior. The collision may have distributed foreign materials deep into the planet's core and mantle regions. These embedded remnants may continue to influence the planet's behavior billions of years later. The impactor essentially became a permanent part of Uranus. Rather than creating debris that scattered through space, the collision produced a single transformed world that preserves evidence of both objects. Modern supercomputers can recreate the Uranus collision in extraordinary detail. These simulations model every aspect of the impact from initial approach to final outcome. The results closely match Uranus's observed characteristics. The simulations reveal the collision sequence step by step. The impactor approached at high speed and struck Uranus at the calculated angle. The impact transferred enormous amounts of rotational energy in a fraction of a second. Within hours of the collision, Uranus had acquired its new sideways orientation. The planet's moons and rings would then have evolved toward the new rotational axis. Material ejected during the impact may have contributed to additional satellites. These computer models can only reproduce Uranus's current state by including the massive collision. Alternative scenarios consistently fail to generate the observed rotation, moon system, and internal structure. The simulations provide a time machine that lets scientists witness the most important event in Uranus's history. They confirm that a single catastrophic impact transformed a normal planet into the sideways world we observe today. Scientists tested every possible alternative to the collision hypothesis. None of them can explain Uranus's extreme characteristics. The process of elimination leaves the massive impact as the only viable explanation. Some researchers proposed that multiple smaller impacts gradually tilted Uranus over time. Computer models show this scenario is physically impossible. The cumulative effects of small collisions cannot generate enough rotational change. Others suggested that gravitational interactions with migrating planets could have tilted Uranus. Detailed calculations reveal that such interactions are far too weak. Even the largest planetary migrations cannot produce the observed effects. A third alternative involved capture of Uranus by a passing star or rogue planet. This scenario also fails mathematical scrutiny. The gravitational forces required would have ejected Uranus from the solar system entirely. Each failed alternative strengthens the case for the collision theory. The massive impact remains the only explanation that satisfies all observational constraints and physical laws. Uranus's collision fits perfectly into the broader story of solar system formation. Similar catastrophic impacts shaped other planets during the same chaotic period. The collision represents typical rather than exceptional planetary evolution. The Moon formed from a similar giant impact on Earth. Mars shows evidence of massive collisions that stripped away much of its atmosphere. Mercury may have lost most of its original mantle to impact processes. Giant impacts were the norm rather than the exception during planetary formation. The early solar system contained hundreds of planetary-sized objects that gradually collided and merged into the final configuration we observe today. Uranus simply preserved the clearest evidence of this violent formation process. While other planets recovered from their collisions or experienced subsequent changes, Uranus maintained its impact-driven configuration for billions of years. The collision that created sidewayness represents a perfectly ordinary event in the context of planetary formation. The extraordinary aspect is not that it happened, but that the evidence remains so clearly preserved. Imagine your compass spinning wildly and pointing in random directions. That is exactly what happens around Uranus. The planet's magnetic field behaves like a broken cosmic compass. Every other planet with a magnetic field follows the same basic rule. The magnetic poles line up roughly with the spinning poles. Earth works this way. Jupiter works this way. Even tilted Saturn follows this pattern. A magnetic field is like an invisible force bubble around a planet. Think of it as the same force that makes magnets stick to your refrigerator, but on a planetary scale. This field protects planets from harmful space radiation. Uranus shatters this magnetic rule completely. The planet's magnetic axis tilts 60 degrees away from its rotation axis. That is like having a compass needle that permanently points sideways instead of north. This creates the most chaotic magnetic environment in the solar system. As Uranus spins, its magnetic field tumbles through space like a cosmic corkscrew. Nothing else in our solar system behaves this way. The ancient collision did not just knock Uranus sideways. It scrambled the planet's magnetic system so thoroughly that it never recovered. Most planets generate their magnetic fields in their centers. Picture Earth's magnetic field originating from deep within the planet's core. Uranus breaks this pattern in the most extreme way possible. The magnetic center of Uranus sits nowhere near the planet's actual center. Instead, it is offset by roughly 1/3 of the planet's radius. Imagine Earth's magnetic field being generated from somewhere beneath the Pacific Ocean instead of the planet's core. This off-center magnetic field creates a lopsided force bubble around Uranus. One side of the planet experiences much stronger magnetism than the other side. The magnetic strength varies dramatically depending on location. Scientists call this an offset dipole configuration. A dipole is simply a magnet with two poles, like a bar magnet. But Uranus's magnetic dipole sits in completely the wrong location. This bizarre arrangement affects everything around the planet. Charged particles from space get trapped in twisted patterns. The magnetic field provides no stable reference point for navigation or orientation. The misplaced magnetic center suggests that Uranus's interior structure was fundamentally altered by the ancient collision. Deep inside Uranus lies one of the strangest magnetic generators in the solar system. The planet creates its magnetic field in the most unlikely place possible. This discovery revolutionized our understanding of planetary magnetism. Most planets generate magnetism in their hot, metallic cores. Molten iron swirls around, creating electric currents that produce magnetic fields. Scientists call this process a dynamo, like the generator in a bicycle wheel. Uranus operates completely differently. The planet generates its magnetic field in the outer layers, not the core. These regions contain electrically conductive water mixed with ammonia and methane. Think of it as a slushy ocean that can carry electric current. This water-ammonia mixture sits much closer to the surface than a traditional magnetic core. The conductive slush moves around as the planet rotates, generating the twisted magnetic field we observe. No other planet uses this type of magnetic generation system. The discovery forced scientists to completely rethink how planetary magnetic fields can form and function. The collision that tilted Uranus apparently created the perfect conditions for this exotic magnetic process to develop. Watch Uranus's magnetic field for a full rotation, and you will see something impossible. The magnetic poles do not stay in fixed positions like they do on other planets. Instead, they spiral around the planet like a cosmic drill bit. As Uranus completes one rotation, its magnetic field corkscrews through space. The magnetic poles trace out complex paths that change constantly. This creates a magnetic environment unlike anything else in the solar system. For comparison, Earth's magnetic field stays relatively stable during rotation. The magnetic North Pole might wander slightly, but it remains roughly in the same general area. Uranus's magnetic poles dance all over the place. This rotating magnetic chaos affects everything in Uranus's vicinity. Spacecraft approaching the planet encounter constantly changing magnetic conditions. Navigation becomes extremely challenging when the magnetic reference points keep moving. The corkscrew pattern results from the combination of Uranus's sideways rotation and its offset magnetic field. These two factors work together to create maximum magnetic confusion. Scientists need sophisticated computer models just to predict where Uranus's magnetic poles will be pointing at any given moment. Inside Uranus, hot material rises and cool material sinks in tilted patterns that do not exist anywhere else. This process, called convection, normally creates organized magnetic fields. In Uranus, it creates magnetic chaos instead. Convection works like a lava lamp. Hot material rises to the top, cools down, then sinks back to the bottom. In most planets, this creates orderly circulation patterns that generate stable magnetic fields. The ancient collision tilted everything inside Uranus at strange angles. Now the convection currents flow in directions that do not match the planet's rotation. Hot material rises sideways instead of straight up. These tilted convection patterns interact with Uranus's sideways rotation to create the scrambled magnetic field. It is like trying to stir soup while the pot is tilted at a crazy angle. Nothing moves in predictable directions. This chaotic internal circulation explains why Uranus's magnetic field changes so dramatically. The underlying engine that creates the magnetism operates in a fundamentally unstable configuration. The planet essentially runs a magnetic generator that is permanently broken but somehow still functional. When the solar wind hits Uranus's twisted magnetic field, it creates some of the most chaotic space weather in the solar system. The interaction produces magnetic tornadoes that would be impossible around any other planet. Solar wind consists of charged particles streaming out from the sun at tremendous speeds. When this wind encounters a planetary magnetic field, it typically gets deflected in predictable patterns. Uranus creates complete chaos instead. The planet's tumbling magnetic field constantly changes how it interacts with the solar wind. Sometimes the field blocks the particles effectively. Other times it funnels them directly toward the planet's surface. This creates a magnetosphere that looks like a cosmic tornado. The boundary between Uranus's magnetic field and the solar wind twists and writhes constantly. No other planet produces such violent space weather. These chaotic interactions affect the entire Uranian system. The twisted magnetosphere influences the planet's aurora displays, radiation belts, and even the behavior of its moons. For future spacecraft visiting Uranus, this magnetic chaos represents one of the most serious navigation and safety challenges. Earth's aurora displays follow predictable patterns around the magnetic poles. Uranus creates aurora chaos that appears in completely unexpected locations. These light shows defy every rule of aurora physics. Aurora occur when charged particles from space collide with a planet's atmosphere. The particles follow magnetic field lines down to the polar regions, creating the familiar curtains of light we see on Earth. Uranus's twisted magnetic field sends these particles in all directions. Aurora appear at random latitudes instead of being confined to polar regions. The lights move around the planet in unpredictable patterns. During some rotations, aurora appear near what we would consider the planet's equator. During other rotations, they show up at completely different locations. The patterns change constantly as the magnetic field corkscrews through space. These chaotic aurora displays provide visible evidence of Uranus's magnetic dysfunction. The lights serve as cosmic indicators of the scrambled magnetic field structure. Observing Uranus's aurora requires sophisticated space telescopes because displays are so unpredictable and scattered across the planet. Uranus's already chaotic magnetic field may be becoming even more unstable as the planet ages. The magnetic system shows signs of further instability that could eventually weaken it substantially. As Uranus slowly cools over billions of years, the internal processes that generate the magnetic field may gradually weaken. The water-ammonia mixture that creates the magnetism could lose energy and become less conductive. This cooling process could eventually disrupt the exotic magnetic generation system. If the conductive slush stops moving effectively, Uranus could lose much of its magnetic field. Computer models suggest the magnetic field strength may have already decreased significantly since the planet's formation. The chaotic nature of the field makes it inherently unstable compared to traditional planetary magnetic systems. Without a magnetic field, Uranus would become far more vulnerable to solar radiation and cosmic particles. The planet's atmosphere could become more exposed to the solar wind. Uranus represents a magnetic system under strain, struggling to maintain basic functionality while slowly moving toward greater instability. How long does winter last on Uranus? Try 21 Earth years. That's longer than most people's entire careers. A single season on this sideways world spans more than 2 decades. On Earth, we experience 4 seasons in 1 year: spring, summer, autumn, winter, each lasting about 3 months. This familiar cycle governs everything from agriculture to fashion to human psychology. Uranus operates on a completely different timescale. The planet takes 84 Earth years to orbit the Sun once. Divide that by 4 seasons and you get seasons that last 21 years each. Imagine experiencing the same season for your entire childhood and teenage years. This extended seasonal cycle affects everything about the planet. Weather patterns, atmospheric chemistry, and surface conditions all change on these incredibly slow timescales. No other planet in our solar system experiences such prolonged seasonal extremes. The sideways rotation that creates these marathon seasons means that entire generations of humans pass away before Uranus completes a single seasonal transition. During Uranus's summer, one pole receives continuous sunlight for 21 straight years. No sunset, no night. Just endless daylight beating down on the same hemisphere for 2 decades. Think about the longest summer day you've ever experienced. Maybe 16 hours of daylight during midsummer. Now imagine that day lasting for 21 years without interruption. That's what happens at Uranus's summer pole. This continuous illumination should create extreme heating effects. The same region gets bombarded with solar energy year after year with no nighttime cooling periods. Basic physics suggests these areas should become extremely hot. Meanwhile, the opposite pole experiences the exact opposite condition. Complete darkness for 21 years straight, no sunlight, no warmth from the sun, just the cold vacuum of space and whatever heat the planet generates internally. These extreme lighting conditions create the most dramatic day-night cycle in the solar system. One hemisphere basks in eternal summer while the other endures endless winter darkness. Here's what should happen on Uranus during these extreme seasons. The summer pole should be scorching hot. The winter pole should be frozen solid. The temperature difference should be enormous. Here's what actually happens. The planet maintains nearly equal temperatures everywhere. Summer and winter poles stay within a few degrees of each other. This seems to defy basic expectations about how planets should behave. Scientists call this temperature distribution. Most planets show dramatic temperature variations between their hot and cold regions. Earth's poles are much colder than the equator. Mars shows similar patterns. Uranus somehow evens out these temperature extremes. The planet acts like a giant heat-distributing machine that keeps conditions surprisingly uniform despite receiving wildly different amounts of sunlight in different regions. This temperature stability suggests powerful atmospheric processes are redistributing heat around the planet. The question is how this heat distribution system works so effectively. Uranus's atmosphere acts like a giant heat redistribution system. Powerful winds carry warmth from the sunlit regions to the dark areas. This creates a planetary heating system that seems difficult to explain. The planet's thick atmosphere contains layers of hydrogen, helium, and other gases. These atmospheric layers can hold enormous amounts of heat energy. Think of the atmosphere as a giant thermal blanket wrapped around the planet. As different regions receive varying amounts of sunlight, the atmosphere responds by moving heat around. Warm air rises from heated areas and flows toward cooler regions. Cold air sinks and flows back toward the warm zones. This atmospheric circulation creates planet-wide wind patterns that operate on massive scales. The winds transport heat across thousands of kilometers, effectively air conditioning the entire planet. The system works so efficiently that seasonal temperature differences get smoothed out almost completely. The atmosphere essentially acts as a planetary thermostat that prevents extreme heating or cooling. Clouds on Uranus form and disappear according to the planet's 21-year seasonal cycle. These cloud systems operate on timescales that dwarf any weather patterns on Earth. The planet's clouds consist primarily of methane ice crystals. Methane is a gas that freezes at extremely cold temperatures. When atmospheric conditions are right, this methane condenses into ice crystals that form visible clouds. During the long summer seasons, increased solar heating changes the atmospheric chemistry. More methane gets converted into gas form, reducing cloud formation in some regions while increasing it in others. These seasonal cloud changes happen so slowly that early astronomers couldn't detect them. You need decades of continuous observation to see Uranus's weather patterns evolve. The cloud formations provide visible evidence of the planet's atmospheric response to its extreme seasonal heating. The patterns serve as long-term weather indicators for this sideways world. Uranus's atmosphere undergoes chemical changes that operate on the 21-year cycles. These reactions respond to the varying amounts of solar radiation different regions receive during the extended seasons. Solar ultraviolet light breaks apart methane molecules in the upper atmosphere. This process, called photodissociation, creates other chemical compounds like ethane and acetylene. Think of it as solar-powered chemistry. During the long polar summers, Specific regions get bombarded with ultraviolet radiation for 21 continuous years. This sustained radiation exposure drives chemical reactions that would be impossible under normal seasonal conditions. The chemical products from these reactions build up over decades. By the time seasonal conditions change, the atmospheric chemistry has been completely altered. Different regions develop distinct chemical signatures based on their sunlight exposure history. These atmospheric chemistry changes affect everything from cloud formation to the planet's color. The chemical composition creates Uranus's distinctive blue-green appearance that subtly shifts over decades. Uranus receives incredibly uneven energy input from the Sun due to its sideways orientation. Yet somehow the planet maintains stable overall energy balance. This seems inconsistent with basic planetary expectations. Energy balance means the amount of energy a planet receives from the Sun roughly equals the energy it radiates back to space. Most planets achieve this balance through fairly even heating across their surfaces. Uranus gets heated in completely lopsided patterns. During summer, one hemisphere gets blasted with continuous sunlight while the other receives none. This should create massive energy imbalances that could destabilize the planet. Instead, the planet's internal systems compensate for these uneven inputs. The atmosphere and internal heat sources work together to maintain overall stability despite the chaotic energy distribution. This energy balancing act requires sophisticated planetary processes that operate on multiple timescales simultaneously. The planet essentially performs constant energy management to prevent severe instability. Predicting weather on Uranus requires forecasting models that span decades instead of days. This creates unprecedented challenges for planetary meteorologists trying to understand the planet's climate patterns. Earth weather operates on timescales of hours to weeks. Weather forecasters can predict conditions a few days in advance with reasonable accuracy. Beyond that, the complexity becomes overwhelming. Uranus weather systems evolve over years and decades. Storm systems develop slowly, persist for extended periods, then gradually dissipate. A single weather pattern might last longer than a human generation. Computer models struggle to simulate these extended timescales. The calculations require enormous computing power to track atmospheric changes over 21-year seasonal cycles. Most existing weather modeling systems aren't designed for such extended predictions. Understanding Uranus's weather requires a completely different approach to meteorology that combines rapid atmospheric processes with ultra-slow seasonal evolution. Scientists can predict Uranus's seasonal progression for centuries into the future. The planet's orbital mechanics are so well understood that astronomers know exactly when each pole will experience its next summer or winter. Currently, Uranus is approaching its autumn equinox. This means both poles are starting to receive more equal amounts of sunlight after decades of extreme seasonal differences. The transition will continue for several more years. By the 2030s, the planet will reach true seasonal balance with both poles receiving similar illumination. This represents the midpoint between the extreme summer and winter conditions. The next major seasonal transition won't occur until the 2040s, when the opposite pole begins its 21-year summer cycle. These predictable transitions allow scientists to plan long-term observation campaigns. Future generations of astronomers will witness seasonal changes on Uranus that no human has ever observed before. The planet's century-spanning cycles ensure that each human generation sees different seasonal phases. Every giant planet in our solar system glows with internal heat. Every giant planet except Uranus. This ice giant seems to violate one of the most familiar patterns in planetary physics. Jupiter radiates more than twice the energy it receives from the Sun. Saturn does nearly the same thing. These massive worlds generate tremendous amounts of internal heat and pump it out into space like cosmic furnaces. Internal heat comes from deep inside a planet's core. Think of it like the warmth from a wood-burning stove. The planet creates its own heat through various processes, then radiates that warmth outward through space. Uranus breaks this pattern completely. The planet emits almost exactly the same amount of energy it receives from sunlight. It's like a house that doesn't have any heating system and relies entirely on whatever sunshine comes through the windows. For a planet this massive, such cold behavior should be extremely unusual. Giant planets are supposed to be hot on the inside. The ancient collision didn't just knock Uranus sideways. It may also have helped shut down much of the planet's internal heating system for the long term. Giant planets generate heat through a process called gravitational compression. As these massive worlds formed, gravity squeezed their materials tighter and tighter. This squeezing action creates enormous amounts of heat energy. Imagine pressing down on a bicycle pump really hard. The air inside gets compressed and becomes hot. Now imagine that same process happening on a planetary scale with thousands of times more pressure. That's how giant planets normally generate internal heat. This compression heating should continue for billions of years. The heat gets trapped deep inside the planet and slowly leaks out to the surface. Most giant planets still glow from heat generated during their original formation. Uranus somehow lost much of this primordial heat source. The planet should still be radiating warmth from its formation 4.6 billion years ago. Instead, it runs cold like a machine with its engine shut off. The absence of this fundamental heat source makes Uranus the coldest giant planet in the solar system. Without strong internal heating, the planet depends much more on distant sunlight for warmth. The ancient collision didn't just tilt Uranus sideways. It may have scrambled the planet's interior structure so thoroughly that heat cannot escape normally. The impact may have created natural insulation that traps any remaining warmth deep below the surface. Most planets have layered interiors that allow heat to flow upward efficiently. Hot material rises from the core while cooler material sinks back down. This process, called convection, works like a planetary heating system. Uranus appears to have a much more complex internal structure. The collision may have mixed different materials together in ways that block normal heat flow. It's like having a house where all the heating ducts got tangled together during construction. Scientists think the impact may have created stable layers inside Uranus that don't mix with each other. Hot material gets trapped in lower layers while cooler material stays near the surface. The heat has nowhere to go. This stratified interior acts like cosmic insulation. Any heat generated deep inside the planet gets blocked from reaching the surface, where it could radiate out into space. The collision may have essentially installed a planetary thermostat that's permanently stuck in the off position. Inside Uranus, different materials may have separated into distinct layers that don't interact with each other. This separation may prevent the mixing that normally helps heat move through planetary interiors. Most giant planets have churning interiors where different materials constantly mix together. This mixing helps move heat upward. Think of it like stirring ingredients in a hot soup. The motion keeps the warmth moving through the liquid. The collision appears to have sorted Uranus's interior materials by weight and density. Heavier rocks and metals sank to the bottom. Lighter ices and gases floated to the top. These separated layers may now stay isolated from each other. Without mixing, heat gets trapped more easily inside different layers. The planet's interior has become as inactive as a perfectly organized filing cabinet. This chemical separation may help explain why Uranus generates so little internal heat compared to other giant planets. The materials that could help move warmth through the interior may be permanently kept apart by the collision's aftermath. Most planets generate at least some heat through radioactive decay. Certain elements naturally break apart over time and release energy in the process. Uranus may contain fewer of these heat-generating elements than some other planets. Radioactive decay works like a cosmic battery that runs for extremely long periods. Elements like uranium and thorium slowly decompose and release heat energy. This process continues for billions of years, providing a steady internal heat source. Earth generates significant heat this way. The warmth from radioactive decay in Earth's interior drives volcanic activity and keeps the planet's core molten. Giant planets may also receive some contribution from radioactive heating deep inside. Uranus may have missed out on accumulating as much of these radioactive materials during its formation. The planet either formed in a region of space with fewer such elements, or the collision somehow changed how these materials were distributed in the interior. Without much radioactive heat, Uranus lacks one of the energy sources that can help keep a planet warm. The planet essentially runs on a depleted cosmic battery. The missing radioactive elements may represent another piece of Uranus's cooling puzzle that traces back to its violent formation history. Jupiter and Saturn stay warm through a process called helium rain. This might sound like science fiction, but it's a real phenomenon that generates enormous amounts of heat. Uranus apparently cannot create the same kind of warming rain. In the deep interiors of some giant planets, helium separates from hydrogen and falls toward the center like metallic raindrops. This helium rain releases gravitational energy that gets converted into heat. It's like a planetary power generator that runs continuously. The helium rain process requires specific temperature and pressure conditions to work properly. The helium must be able to condense into droplets and fall through the hydrogen atmosphere. This creates a constant source of internal heating. Uranus's scrambled interior apparently cannot support this helium rain process. Either the conditions aren't right for helium to condense, or the internal structure prevents the rain from falling properly. Without helium rain, Uranus misses out on a major heat source that keeps some other giant planets warm. The planet lacks this cosmic heating system that can operate automatically in a massive world. The absence of helium rain may represent yet another way the ancient collision permanently altered Uranus's ability to generate internal heat. Even if Uranus generates some internal heat, the planet's unusual structure prevents that warmth from reaching the surface. The scrambled interior acts like a thermal barrier that blocks heat flow. Heat transfer in planetary interiors normally works through convection currents. Hot material rises upward while cool material sinks downward. This circulation carries heat from the core to the surface where it can radiate into space. Uranus appears to have disrupted convection pathways throughout its interior. The collision created a complex internal structure where heat cannot flow upward efficiently. Warm areas get isolated from the surface by layers of cooler material. It's like having a house where all the heat ducts are blocked with insulation. The furnace might be working in the basement, but none of that warmth can reach the living areas upstairs. This thermal isolation means any heat generated deep inside Uranus gets trapped there for extremely long periods. The warmth cannot escape to the surface where spacecraft and telescopes could detect it. The planet essentially suffers from cosmic hypothermia. It is unable to circulate its own body heat effectively. Uranus operates more like a solar panel than a traditional giant planet. Almost all of its detectable warmth comes directly from sunlight rather than strong internal heat sources. This makes it unique among giant planets. For comparison, Jupiter receives only tiny amounts of energy from the distant sun. Most of Jupiter's warmth comes from internal processes. The planet could maintain much of its current temperature pattern, even if the sun disappeared entirely. Uranus would become even colder without the sun's energy. The planet has no significant internal heating to maintain its temperature independently. It depends heavily on solar radiation for warmth. This solar dependence makes Uranus much more sensitive to its distance from the Sun. Small changes in orbital distance would affect the planet's temperature more strongly. Other giant planets would notice such variations much less. The reliance on solar heating also means Uranus experiences much slower temperature responses. When seasonal heating patterns change, it takes the planet much longer to adjust because there's so little internal heat source to buffer the temperature changes. Uranus essentially operates as the solar system's largest solar-powered device, a cosmic machine that runs almost entirely on energy from space. Uranus's thermal problems will only get worse with time. The planet continues to lose whatever small amounts of internal heat it still possesses. Eventually, it will become even colder and more dependent on solar energy. Over billions of years, planets naturally cool down as they radiate heat into space. Most giant planets can maintain reasonable temperatures because they generate new heat internally through various processes. Uranus lacks most of these heat-generating mechanisms. The planet is essentially cooling toward equilibrium with its surroundings over cosmic timescales, without strong internal heat sources to replace the energy being lost. Uranus will gradually become colder still. This continued cooling will affect every aspect of the planet's behavior. Atmospheric activity will slow down even further. Chemical processes will become less active. The planet's ability to maintain its current atmospheric structure may eventually be compromised. Uranus represents a giant planet in thermal decline, slowly freezing its way toward deeper equilibrium with the cold vacuum of space. Uranus teaches us that planetary heating systems can be permanently damaged by catastrophic events. The ice giant serves as an example of what happens when a planet's internal heat sources get disrupted beyond easy repair. Most planetary scientists assumed that giant planets would naturally maintain internal heat sources throughout their lifetimes. The assumption seemed reasonable based on observations of Jupiter and Saturn, which both show strong internal heating. Uranus proves this assumption wrong. Under the right circumstances, a planet can lose much of its ability to generate internal heat. The thermal shutdown can be so complete that the planet never fully recovers. This lesson has important implications for understanding planets around other stars. Many of the exoplanets discovered so far are similar in size to Uranus. Some of them may have experienced similar collision histories that shut down their heating systems. Uranus demonstrates that planetary thermal evolution can take dramatically different paths depending on the violence of formation events. Sometimes the most important aspect of a planet's development is not what happened during normal formation, but what went catastrophically wrong. Look at any planet with rings, and you'll see them wrapped around the middle like a belt. Saturn's rings circle its equator in perfect horizontal loops. Jupiter's faint rings do the same thing. Uranus breaks this universal rule completely. The rings of Uranus stand vertically in space. Instead of lying flat around the planet's middle, they stick up like a giant Ferris wheel. When viewed from Earth, these rings appear as thin lines standing on edge. Planetary rings normally form in the equatorial plane. That's the imaginary flat disk that circles around a planet's middle. Think of it like the equator on Earth, but extended out into space as a flat surface where rings and moons naturally settle. Uranus has an equatorial plane too, but it's tilted sideways along with the rest of the planet. The rings faithfully follow this tilted equator, creating a ring system that stands upright instead of lying flat. This vertical orientation makes Uranus's rings nearly impossible to see from certain angles. Sometimes we look at them edge-on, and they practically disappear. Other times we see them face-on, and they appear as complete circles. The sideways rings prove that the entire Uranian system tilted together during the ancient collision. Uranus hosts 27 known moons, and every single one orbits in the same impossible direction. They all circle around the planet's sideways equator, creating a family of satellites that defy normal orbital mechanics. Many regular planetary moons orbit close to their planet's equator. Jupiter's 4 largest moons do this around Jupiter. This creates orderly orbital patterns that make sense from a physics perspective. The moons of Uranus orbit around the tilted equator instead. From our perspective on Earth, these moons appear to orbit vertically like spokes on a spinning wheel that's standing upright. No other planetary system in our solar system works this way. The largest Uranian moon, Titania, demonstrates this bizarre orbital behavior perfectly. Instead of following a sensible horizontal path around the planet, Titania traces out a vertical circle in space. This synchronized tilting of all 27 moons provides powerful evidence for the collision theory. When the ancient impact knocked Uranus sideways, it carried the entire moon system along with it. The moons didn't gradually adjust to new orbital planes. They all tilted together as a complete system, maintaining their original relationships to the planet's equator. The moons of Uranus are gradually spiraling outward from the planet. This process, called tidal evolution, works like a cosmic escalator that slowly carries satellites to higher and higher orbits. Tidal evolution happens because of gravitational interactions between a planet and its moons. The moon's gravity creates slight bulges in the planet's shape. The planet's rotation tries to drag these bulges along, which pulls on the moon and changes its orbit. Over millions of years, this gravitational tugging causes moons to gain energy and move to larger orbits. It's like a cosmic version of a parent pushing a child on a swing. Each gravitational push adds a little more energy to the moon's motion. The process works so slowly that you'd never notice it during a human lifetime. But over geological timescales, moons can migrate significant distances away from their parent planets. Despite the chaotic collision that created the Uranian system, tidal evolution continues to operate normally. The sideways moons follow the same physics laws as moons anywhere else in the solar system. This gradual outward migration will eventually spread Uranus's moons across much larger orbits, creating an even more extended satellite system. Among Uranus's multiple rings, one stands out as the dominant structure. The epsilon ring contains most of the ring material and displays the most complex behavior. This ring system operates like a cosmic traffic control system. The epsilon ring is both the brightest and narrowest of Uranus's rings. While other rings appear faint and diffuse, the epsilon ring shows up clearly in telescopic observations. It contains dense concentrations of ring particles that reflect sunlight efficiently. This dominant ring maintains its structure through the help of shepherd moons. These are small satellites that orbit just inside and outside the ring. Their gravity acts like cosmic bumpers that keep ring particles from spreading out too much. The shepherd moons work like invisible boundaries that coral the ring particles. When particles try to drift inward or outward, the shepherd moon's gravity nudges them back into place. This creates a stable ring structure that can persist for millions of years. Without these shepherd moons, the epsilon ring would gradually spread out and disappear. The gravitational shepherding process keeps the ring particles organized in a narrow band despite the chaotic forces acting on them. The epsilon ring system demonstrates how complex gravitational interactions can create order even in the sideways Uranian environment. Miranda, one of Uranus's inner moons, displays the most dramatic surface features in the entire solar system. This small world looks like it was broken apart and reassembled multiple times throughout its history. The moon's surface contains a bizarre mixture of terrains that shouldn't exist together. Smooth plains sit right next to jagged cliffs and deep canyons. Some regions look ancient and heavily cratered, while others appear surprisingly young and unmarked. Miranda's most striking features are its corona, strange circular regions that look like giant geological scars. These formations suggest the Moon experienced catastrophic disruption events that partially melted and reformed its surface. Scientists think Miranda suffered multiple collisions throughout its history. Each impact heated and deformed the little Moon, creating new geological features while preserving evidence of previous catastrophes. The Moon's small size makes its complex geology even more puzzling. Miranda should have cooled down quickly after formation and remained geologically inactive. Instead, it shows clear evidence of recent geological activity. Miranda serves as a record of the violence that characterized the early Uranian system, preserving evidence of the collisions that shaped all the sideways satellites. Some of Uranus's moons maintain precise gravitational relationships with each other called orbital resonances. These cosmic synchronizations keep certain satellites locked in perfectly timed orbital dances. An orbital resonance occurs when two moons complete their orbits in exact mathematical ratios. For example, one moon might complete exactly 2 orbits while another completes 3 orbits. This creates a repeating pattern of gravitational interactions. These synchronized orbits work like a cosmic clockwork mechanism. Every time the moons reach certain positions relative to each other, they exchange gravitational energy in predictable patterns. This helps stabilize their orbits over long periods. The resonant relationships prevent the moons from colliding with each other even though they orbit in the same tilted plane. The gravitational synchronization acts like a cosmic traffic control system that manages satellite spacing. Several pairs of Uranian moons participate in these resonant relationships. The gravitational coordination helps maintain the stability of the entire satellite system despite its unusual sideways orientation. These orbital resonances demonstrate that even in the chaotic aftermath of the ancient collision, gravitational physics still operates according to predictable mathematical principles. William Herschel discovered Uranus in 1781, but finding the planet's moons took much longer. The satellites were so faint and distant that astronomers needed increasingly powerful telescopes to detect them over 2 centuries. Herschel himself discovered the first 2 moons, Titania and Boron, in 1787. These largest satellites were bright enough to see with the telescopes available at that time. But detecting the remaining 25 moons required technological advances that wouldn't come for decades. The discovery process stretched across more than 200 years. Each new generation of telescopes revealed fainter and smaller moons orbiting at greater distances from Uranus. The most recent discoveries came from sophisticated space-based observatories and advanced computer image processing. Many of the outer moons weren't discovered till the late 20th and early 21st centuries. These distant satellites are so small and faint that they remained invisible to earlier generations of astronomers. The gradual revelation of Uranus's moon system mirrors the general pattern of astronomical discovery. Each technological advance allows scientists to probe deeper into previously invisible realms. The complete census of Uranian satellites probably isn't finished yet. Future telescopes may reveal even more moons orbiting in the outer reaches of the tilted system. Uranus's moons follow a unique naming convention that sets them apart from every other planetary system. Instead of using names from Greek or Roman mythology, these satellites bear names from English literature. Most of the moons are named after characters from Shakespeare's plays. Titania and Oberon come from A Midsummer Night's Dream. Miranda derives from The Tempest. Ariel appears in the same play as a magical spirit character. Additional moons bear names from works by Alexander Pope, particularly The Rape of the Lock. This creates a moon system with a distinctly English literary flavor that reflects the planet's discovery by British astronomer William Herschel. The naming tradition continues with each new moon discovery. Astronomers maintain the literary theme, by selecting appropriate character names from classic English works. This literary naming system makes Uranus's satellites easy to remember for anyone familiar with classic literature. The names also reflect the cultural context of the planet's discovery during the height of English literary achievement. The Shakespearean moon names add a touch of artistic elegance to what is essentially a collection of cold, rocky worlds orbiting a sideways ice giant. Uranus's 27 moons display an enormous range of sizes, from substantial worlds comparable to Earth's moon down to tiny objects barely larger than city blocks. This size distribution tells the story of how the satellite system formed and evolved. Titania, the largest Uranian moon, measures about 1,600 kilometers in diameter. That makes it roughly half the size of Earth's moon and large enough to have experienced significant geological evolution throughout its history. The smallest confirmed moons are only a few kilometers across. These tiny satellites are probably captured asteroids or fragments left over from ancient collisions. They're too small to have developed spherical shapes under their own gravity. Between these extremes lie moons of intermediate sizes that show varying degrees of geological complexity. The larger satellites retain enough internal heat to drive geological processes, while the smaller ones remain frozen and inactive. This size hierarchy reflects the violent history of the Uranian system. Large moons survived the collision events that created the system, while small moons represent debris and fragments from those same catastrophic impacts. The diverse moon sizes ensure that Uranus's satellite system contains examples of almost every type of small world found throughout the solar system. Almost all of Uranus's moons have surprisingly dark surfaces that reflect very little sunlight. These charcoal-colored worlds absorb most of the light that hits them, creating a collection of shadow satellites around the ice giant. For comparison, Earth's moon reflects about 12% of the sunlight that strikes it. Most Uranian moons reflect only 5 to 7% of incoming light. Some are even darker, reflecting less than 3% of the sunlight. The dark coloration suggests these moons contain significant amounts of organic compounds or carbon-rich materials. These substances absorb light efficiently and give the surfaces their coal-black appearance. Scientists think the dark materials accumulated on the moon's surfaces over billions of years. Cosmic radiation may have altered the surface chemistry, creating complex organic molecules that absorb light across all wavelengths. The uniformly dark appearance of most Uranian moons suggests they all experienced similar surface evolution processes. Whatever mechanism darkened their surfaces operated throughout the entire satellite system. These mysterious dark surfaces hide the detailed compositions of the Uranian moons, making them some of the most poorly understood objects in the outer solar system. The Uranian satellite system continues to evolve through tidal forces and gravitational interactions. Over millions and billions of years, the current arrangement of moons and rings will change dramatically. Tidal evolution will continue pushing the larger moons outward to more distant orbits. Eventually, some satellites may migrate so far from Uranus that they escape the planet's gravitational influence entirely. The ring system will also evolve over time. Ring particles constantly collide with each other, gradually grinding down into smaller pieces. Some material will spiral inward and crash into Uranus, while other particles may be ejected from the system. New moons may form from ring material that accumulates in gravitationally stable regions. The process that created some of the current satellites from collision debris could repeat itself with different outcomes. The overall architecture of the Uranian system will slowly transform as gravitational forces continue reshaping orbital relationships. Future astronomers billions of years from now would observe a satellite system quite different from what we see today. This ongoing evolution ensures that Uranus's sideways family of moons and rings represents just one snapshot in a continuously changing cosmic drama. Why doesn't Uranus have extreme temperature differences between its poles? The planet receives wildly uneven heating from the Sun due to its sideways orientation. Yet somehow the temperatures stay remarkably similar everywhere. During the 21-year polar summers, one hemisphere gets blasted with continuous sunlight while the other pole sits in total darkness. Basic physics says the sunny side should be much warmer and the dark side should be much colder. Instead, Uranus maintains nearly equal temperatures across its visible atmosphere. The difference between the hottest and coldest regions amounts to only a few degrees. This temperature uniformity defies everything scientists know about planetary heating. Most planets show dramatic temperature variations based on sunlight exposure. Earth's poles are much colder than the equator. Mars displays similar temperature gradients based on latitude and season. Uranus somehow operates a planetary air conditioning system that redistributes heat so efficiently that extreme heating gets smoothed out completely. The atmosphere acts like a giant thermal blanket that keeps temperatures stable despite chaotic energy input. The planet's unique atmospheric circulation must be incredibly efficient at moving heat around to maintain such remarkable temperature balance. The atmosphere of Uranus consists of multiple layers that work together like a giant mixing bowl. These atmospheric layers contain hydrogen, helium, and other gases that can hold and transport enormous amounts of heat energy. Think of Earth's atmosphere as a thin skin wrapped around the planet. Uranus has a much thicker atmospheric envelope that extends deep into the planet's interior. This thick atmosphere can store vastly more heat than the thin air layers around rocky planets. The atmospheric composition includes roughly 83% hydrogen and 15% helium. The remaining 2% contains water, methane, and ammonia ices that give Uranus its distinctive blue-green color. These different gases don't just sit in separate layers. They mix and circulate through complex atmospheric currents that operate on planetary scales. Hot gases rise from deeper levels while cooler gases sink back down, creating massive circulation patterns. This atmospheric mixing process works like a planetary scale conveyor belt that constantly redistributes heat. The circulation system ensures that no region gets too hot or too cold compared to the rest of the planet. The thick, active atmosphere essentially functions as Uranus's temperature control system. Given Uranus's extreme seasonal heating, the planet should experience violent atmospheric storms and chaotic wind patterns. Instead, it displays some of the calmest and most predictable atmospheric behavior of any giant planet. Jupiter and Saturn host massive storm systems with winds reaching hundreds of kilometers per hour. These giant planets generate powerful hurricanes that can persist for decades or centuries. Their atmospheres churn with constant violent activity. Uranus operates completely differently despite having all the ingredients for extreme weather. The planet shows only gentle atmospheric circulation and modest wind speeds. Storm systems remain relatively small and short-lived compared to other giant planets. The atmospheric calm results partly from Uranus's lack of internal heat. Without energy rising from the planet's interior, weather systems lack the power source needed for violent activity. The atmosphere runs almost entirely on weak solar heating. This creates a weather system that changes slowly and predictably rather than generating the chaotic storms seen on other worlds. Uranus essentially experiences cosmic weather that operates in slow motion. The planet's atmospheric tranquility makes it one of the most meteorologically boring giant planets in the solar system. Uranus's atmosphere undergoes slow chemical transformations that follow the planet's 21-year seasonal cycles. These chemical changes respond to varying amounts of solar ultraviolet radiation that different regions receive during the extended seasons. Methane gas in the upper atmosphere gets broken apart by solar ultraviolet light in a process called photodissociation. Think of it as solar-powered chemistry that creates new molecules from existing ones. The process works like a cosmic chemical factory powered by sunlight. During the long polar summers, specific atmospheric regions get bombarded with ultraviolet radiation for 21 continuous years. This sustained exposure drives chemical reactions that would be impossible under normal seasonal conditions. The chemical reactions produce ethane, acetylene, and other hydrocarbon compounds that gradually accumulate in the atmosphere. These new molecules change the atmospheric composition and affect how the atmosphere absorbs and reflects light. The chemical changes happen so slowly that they operate on generational timescales rather than weather timescales. By the time seasonal conditions shift, the atmospheric chemistry has been fundamentally altered. These chemical transformations contribute to Uranus's distinctive coloration and help explain why the planet appears different from other ice giants. Clouds on Uranus form and dissipate according to processes that operate much more slowly than cloud formation on any other planet. These atmospheric clouds follow the planet's extreme seasonal patterns rather than daily weather cycles. The planet's clouds consist primarily of methane ice crystals that form when atmospheric methane encounters extremely cold conditions. Methane condenses into solid ice particles that create visible cloud formations in the upper atmosphere. Cloud formation depends on atmospheric temperature and pressure conditions that change very slowly on Uranus. Unlike Earth's rapidly changing weather systems, Uranian clouds develop over months or years rather than hours or days. During different seasons, cloud formation patterns shift as atmospheric heating changes. Some regions become more favorable for cloud development, while others see existing clouds gradually evaporate. The slow cloud evolution makes weather prediction on Uranus completely different from terrestrial meteorology. Storm systems that might develop and dissipate in days on Earth could persist for years on Uranus. Observing cloud changes on Uranus requires decades of patient monitoring, rather than daily weather satellite images. Most planets with thick atmospheres experience significant greenhouse effects that trap heat and warm the atmosphere below. Uranus's hydrogen and helium atmosphere provides only a weak greenhouse effect that barely influences the planet's temperature. A greenhouse effect works when an atmosphere traps heat radiation trying to escape upward. Certain gases absorb this heat radiation and re-radiate it back downward, creating additional warming. Earth's atmosphere does this naturally with water vapor and carbon dioxide. Uranus's atmosphere consists mainly of hydrogen and helium, which are poor greenhouse gases. These molecules don't absorb heat radiation efficiently, so most of the planet's thermal energy escapes directly to space without being trapped. The weak greenhouse effect means Uranus gets very little atmospheric warming beyond direct solar heating. The planet essentially operates without the thermal insulation that helps keep other worlds warm. This lack of atmospheric heat trapping contributes to Uranus's status as the coldest giant planet. Without an efficient greenhouse effect, the planet loses heat to space faster than other atmospheric worlds. The minimal greenhouse warming makes Uranus almost entirely dependent on direct solar radiation for its atmospheric temperature. Deep inside Uranus, increasing pressure transforms matter into exotic forms that don't exist anywhere on Earth's surface. These pressure changes create some of the most extreme material conditions in the solar system. As you travel deeper into Uranus, the pressure increases dramatically. Think of it like diving deep underwater, where water pressure grows stronger the deeper you go. But instead of water, you're moving through layers of increasingly compressed material. At extreme depths, the pressure becomes so intense that matter can shift into electrically conductive states. These exotic forms can only exist under enormous pressure conditions. The transition happens gradually over a vast depth range within Uranus. There's no sharp boundary where one state suddenly becomes another, but rather a broad transformation zone. This deep conductive region may contribute to Uranus's unusual magnetic field generation. The electrically conductive material could participate in the complex magnetic processes that create the planet's scrambled magnetic field. The pressure-induced phase transitions make Uranus's deep interior a laboratory for extreme physics that cannot be replicated on Earth. The upper atmosphere of Uranus contains complex haze layers that obscure our view of deeper atmospheric structures. These hazes form from hydrocarbon compounds created by solar radiation and create a permanent atmospheric veil around the planet. Atmospheric haze consists of tiny particles suspended in the air, similar to smog in Earth's cities but made from different chemicals. On Uranus, the haze particles form from hydrocarbon molecules created when solar ultraviolet light breaks apart methane. These hydrocarbon particles clump together into larger droplets that scatter sunlight in all directions. The scattering effect creates a hazy appearance that makes it difficult to see through the atmosphere to deeper layers. The haze layers change thickness and distribution based on seasonal solar heating patterns. Regions receiving more ultraviolet radiation tend to produce thicker hazes that persist for years or decades. This atmospheric haze presents a major challenge for scientists trying to study Uranus's atmospheric structure. Most telescopic observations can only probe the hazy upper layers rather than the clearer atmosphere below. Understanding Uranus's complete atmospheric structure requires sophisticated instruments that can penetrate through the hydrocarbon haze layers. Occasionally, Uranus develops large atmospheric storm systems that appear suddenly and disappear just mysteriously. These storm events provide rare glimpses into the planet's hidden atmospheric dynamics. Most of the time, Uranus appears remarkably calm with very few visible atmospheric features. The planet often looks like a featureless blue-green disk, even through powerful telescopes. This atmospheric tranquility can persist for years without significant changes. Then, without warning, massive storm systems suddenly appear in the atmosphere. These storms can grow to Earth-sized proportions and become bright enough to see from telescopes on Earth. The storms typically persist for several months before gradually fading back to invisibility. Scientists don't understand what triggers these sudden atmospheric outbursts or why they disappear so completely. The storm events may be related to seasonal transitions when atmospheric heating patterns shift dramatically. The changing energy balance might occasionally trigger instabilities that create temporary storm activity. These rare storms provide scientists with their best opportunities to study active weather processes in Uranus's normally placid atmosphere. Studying Uranus's atmospheric changes requires observational campaigns that span multiple human generations. The planet's 84-year orbital period means atmospheric evolution occurs on timescales much longer than individual scientific careers. Most atmospheric research focuses on rapid changes that happen over days, weeks, or seasons. Scientists can study Earth's weather patterns or Jupiter's storm systems and see significant changes during a single research project. Uranus operates on completely different timescales that challenge traditional astronomical observation methods. Meaningful atmospheric changes might take decades to become apparent, requiring sustained monitoring programs that outlast individual researchers. Early observations of Uranus date back to William Herschel's discovery in 1781, but systematic atmospheric monitoring only began in the late 20th century. Even with 240 years of total observation time, the scientists have witnessed less than 3 complete Uranian years. The long-term observational challenge means our understanding of Uranus's atmospheric behavior remains fundamentally incomplete. Future generations of astronomers will observe atmospheric phenomena that no human has ever seen before. Comprehensive atmospheric study of Uranus requires institutional commitment to multi-generational research programs that can track changes across multiple orbital periods. Traditional weather prediction models fail completely when applied to Uranus's sideways atmospheric system. The planet's unique orientation creates atmospheric dynamics that don't exist anywhere else in the solar system. Most atmospheric models assume planets spin upright with normal day-night cycles and predictable seasonal patterns. These models work well for Earth, Mars, and even the giant planets Jupiter and Saturn that follow conventional orientations. Uranus breaks every assumption built into standard atmospheric modeling systems. The planet's sideways rotation creates heating patterns that no existing weather model can handle properly. Computer simulations struggle to predict atmospheric behavior when one pole receives continuous heating for decades while the other pole sits in perpetual darkness. The extreme seasonal imbalance overwhelms computational models designed for normal planetary conditions. Developing accurate weather models for Uranus requires completely new approaches to atmospheric physics that account for the planet's unique geometry and extended seasonal cycles. The modeling challenge represents one of the most complex problems in planetary meteorology, requiring specialized computational tools that don't exist for any other world. Only one spacecraft has ever visited Uranus in the entire history of space exploration. Voyager 2 flew past the giant in 1986, providing humanity's only close-up look at this sideways world. The encounter lasted just a few hours as Voyager 2 raced past Uranus at tremendous speed. Think of it like trying to study an entire city while driving past it on the highway at night. You might see some interesting sights, but you miss most of the important details. Voyager 2's brief visit revealed Uranus's tilted magnetic field, discovered new moons, and confirmed the vertical ring system. But the spacecraft had no time to study seasonal changes, atmospheric chemistry, or internal structure in any meaningful detail. The flyby occurred during Uranus's southern summer, when one pole was pointed almost directly toward the Sun. This timing meant Voyager 2 saw the planet during one of its most extreme seasonal configurations. Most of what we know about Uranus comes from that single encounter about 40 years ago. The limited data has forced scientists to piece together theories based on incomplete information. Uranus remains the least understood planet in our solar system because we've barely begun to explore it properly. Getting to Uranus requires spacecraft journeys that last longer than most people's entire careers. The enormous distance and limited launch opportunities make mission planning incredibly complex. Uranus orbits roughly 19 times farther from the Sun than Earth does. Even traveling at tens of thousands of kilometers per hour, spacecraft need 8 to 13 years to reach the ice giant. That's longer than most graduate students spend earning their degrees. Mission planners must use gravitational assists from other planets to reach Uranus efficiently. This technique uses the gravity of planets like Jupiter to slingshot spacecraft toward their final destination. But the planets align properly for these assists only once every few years. The long journey times mean scientists who design Uranus missions might retire before their spacecraft arrive. Mission teams must plan for personnel changes and technological obsolescence during the extended cruise phases. Current rocket technology cannot launch heavy spacecraft directly to Uranus in reasonable timeframes. Future missions will require either more powerful rockets or innovative propulsion systems to make the journey practical. The distance challenge ensures that every Uranus mission represents a major long-term commitment for space agencies and research institutions. An orbital spacecraft could spend years studying Uranus instead of just hours. This extended observation time would revolutionize our understanding of the planet's seasonal changes, atmospheric dynamics, and internal structure. Unlike a flyby mission that races past the planet, an orbiter would circle Uranus for multiple years. The spacecraft could observe complete seasonal transitions, study storm development, and monitor atmospheric chemistry changes in real time. The orbital mission could map Uranus's gravitational field with extreme precision. This gravity mapping would reveal the planet's internal structure and confirm whether the ancient collision really scrambled the interior as thoroughly as scientists suspect. An orbiter would also study the twisted magnetic field continuously as it corkscrews through space. Long-term magnetic observations could finally explain how this bizarre field system generates and maintains itself. The mission could conduct detailed studies of all 27 moons and the ring system. Close-up observations would reveal surface compositions, geological histories, and orbital evolution patterns impossible to study from Earth. An orbital mission represents the difference between getting a glimpse of Uranus and truly understanding how this sideways world works. Scientists dream of sending a probe directly into Uranus's atmosphere to measure conditions that no telescope can detect from Earth. This atmospheric dive would provide the first direct samples of the ice giant's mysterious atmospheric chemistry. An atmospheric probe works like a scientific parachute that falls through a planet's atmosphere while transmitting data. The Galileo mission used this technique successfully at Jupiter in 1995. Revealing atmospheric composition and structure in unprecedented detail. The Uranus probe would measure atmospheric pressure, temperature, and chemical composition at different depths. These direct measurements would solve mysteries about atmospheric circulation, heat distribution, and chemical processes that drive the planet's weather systems. The probe could determine whether water exists in Uranus's atmosphere, and measure the exact concentrations of methane, ammonia, and other compounds. These chemical measurements would provide crucial clues about how the planet formed and evolved. The atmospheric dive would be a one-way journey lasting several hours as the probe falls deeper into increasingly dense atmospheric layers. Eventually, the extreme pressure would crush the probe, but not before transmitting invaluable atmospheric data. This direct atmospheric sampling would provide ground truth for all the theoretical models scientists have developed about Uranus's atmospheric behavior. Understanding Uranus's complete seasonal cycle requires observations that span 84 Earth years. No single human career is long enough to witness a complete Uranian year from beginning to end. Current seasonal observations cover only fragments of the planet's climate cycle. Astronomers have observed roughly 3 complete seasons since Uranus's discovery in 1781. This limited dataset makes it impossible to understand normal versus abnormal atmospheric behavior. A comprehensive seasonal study would require institutional commitments that outlast individual researchers. Future space agencies would need to plan multi-generational observation programs that continue regardless of personnel changes. The scientific payoff would be enormous. Complete seasonal monitoring would reveal how Uranus's atmosphere responds to extreme heating variations, how storms develop during seasonal transitions, and whether the planet's thermal balance remains stable over long periods. These observations could predict future atmospheric changes and determine whether Uranus's climate system is inherently stable or gradually evolving toward different configurations. Seasonal monitoring represents one of the most challenging observational commitments in planetary science, requiring sustained effort across multiple human generations. Detailed mapping of Uranus's scrambled magnetic field could fundamentally change our understanding of how planetary magnetic systems work. The ice giant's bizarre magnetism challenges basic theories about planetary magnetic field generation. Most magnetic field theories assume planets generate magnetism in their cores through predictable processes. Uranus apparently violates these basic assumptions by creating magnetic fields in the outer layers through completely different mechanisms. Long-term magnetic field monitoring could reveal whether the chaotic field configuration is stable or slowly evolving toward collapse. These observations would determine if Uranus represents a temporary magnetic anomaly or a fundamentally different type of planetary magnetic system. The magnetic studies could also determine whether other ice giants might develop similar field configurations under the right circumstances. This knowledge would help scientists understand magnetic field evolution on planets throughout the galaxy. Precise magnetic measurements might even reveal internal structure details that gravity mapping cannot detect. The twisted magnetic field lines could serve as probes that reveal circulation patterns deep inside the planet. Understanding Uranus's magnetic system could force scientists to completely revise theories about planetary magnetic field generation and evolution. Close-up studies of Uranus's vertical ring system could explain how planetary rings behave under extreme gravitational conditions. The sideways rings provide a natural laboratory for testing ring physics theories. Current ring observations from Earth reveal only basic structural features like brightness and width variations. Detailed spacecraft observations could measure individual ring particle sizes, compositions, and orbital behaviors. Scientists could determine whether the rings formed from shattered moons or accumulated from external debris. Chemical analysis of ring particles would reveal their origin and evolution history. The studies would also investigate how shepherd moons maintain ring structure in the chaotic Uranian gravitational environment. Understanding this shepherding process could explain ring stability around tilted planets. Ring particle collision studies would reveal how material behaves under the unique conditions created by Uranus's sideways rotation and twisted magnetic field. These collision dynamics might operate differently than in normal planetary ring systems. Comprehensive ring analysis would provide insights into ring formation and evolution processes that apply to ring systems throughout the solar system and beyond. Direct measurements of Uranus's internal structure could provide definitive proof that a massive collision created the planet's sideways orientation. Several lines of evidence could confirm or refute the collision theory once and for all. Seismic studies could reveal internal layering patterns that preserve evidence of the ancient impact. Just as geologists study earthquake waves to understand Earth's interior, planetary seismologists could map Uranus's internal structure using gravitational field measurements. Chemical analysis of atmospheric isotope ratios could identify foreign materials incorporated during the collision. Different regions of the early solar system had distinct chemical signatures, so collision debris would show up as contamination in Uranus's atmospheric composition. Detailed thermal modeling could determine whether the planet's internal heat distribution matches collision predictions. The impact should have created specific patterns of heat loss and internal temperature distribution that persist billions of years later. High-resolution gravity mapping could detect internal density variations caused by collision debris settling in different layers. These gravitational anomalies would serve as fossil evidence of the ancient catastrophe. Computer simulations guided by detailed observational data could recreate the collision with sufficient accuracy to confirm specific impact scenarios. Studying Uranus has implications far beyond our solar system, because astronomers have discovered thousands of similar-sized planets orbiting other stars. Understanding Uranus helps us interpret observations of these distant worlds. Neptune-sized exoplanets are among the most common types of planets found around other stars. Many of these worlds might have experienced collision histories similar to Uranus's catastrophic past. Detailed Uranus studies would provide a template for understanding how planetary collisions affect atmospheric evolution, magnetic field generation, and thermal balance on worlds throughout the galaxy. The knowledge gained from Uranus exploration would help astronomers identify collision-altered exoplanets and distinguish them from planets that formed through normal processes. Uranus represents our only opportunity to study a collision-modified ice giant up close. The lessons learned from this sideways world could revolutionize our understanding of planetary evolution throughout the universe. Future exoplanet observations will undoubtedly discover many Uranus-like worlds, making our ice giant a crucial reference point for comparative planetary science. Comprehensive Uranus exploration would establish the ice giant as a cornerstone case study for understanding how catastrophic events shape planetary evolution. The scientific insights would influence planetary research for generations. Current planetary science focuses heavily on Earth like rocky worlds and Jupiter like gas giants. Ice giants like Uranus represent a poorly understood middle category that may be the most common type of planet in the galaxy. Detailed Uranus studies would reveal how planets recover from catastrophic collisions and whether such events create permanent changes or temporary disruptions. This knowledge applies to planetary development throughout cosmic history. The research would also determine whether collision-altered planets can maintain stable conditions suitable for life development. Understanding Uranus's thermal and magnetic evolution could help identify habitable worlds around other stars. Uranus exploration would provide crucial data for computer models that simulate planetary formation and evolution processes. These models guide our understanding of how planetary systems develop throughout the universe. The scientific legacy of comprehensive Uranus exploration would extend far beyond understanding a single sideways planet to revolutionizing our knowledge of planetary science as a whole. Current space agency plans suggest that dedicated Uranus missions could launch within the next 15 years. However, the scientific answers we seek will require decades of patient observation and analysis. Mission planners are working toward a launch window in the early 2030s, when planetary alignments favor efficient trajectories to Uranus. The spacecraft would arrive in the early 2040s and begin multi-year observation campaigns. Initial discoveries would emerge within the first few years of orbital operations, but understanding seasonal changes requires observations spanning multiple decades. Some questions about Uranus's behavior will not be answered until the late 21st century. The collision theory verification could happen relatively quickly through internal structure mapping and chemical analysis. But confirming long-term atmospheric stability patterns will require generational observation commitments. Future technological advances might accelerate some aspects of Uranus research through improved instruments and faster spacecraft propulsion systems. However, the fundamental requirement for long-term observations cannot be shortened. Solving Uranus's deepest mysteries will ultimately require sustained scientific commitment that outlasts individual careers and spans multiple generations of researchers.